Welcome to this explainer. Today, we're diving into FastKey, which is just an incredibly elegant macOS productivity tool. But we aren't only looking at the shiny finished product. We're actually going to explore the chaotic engineering reality of building it across two totally different chip architectures, Apple's M1 and Intel. It's a fascinating case study in massive time saving and the deep technical trade-offs you have to make to get a tool like this to actually work. Okay, let's just quickly look at our roadmap. We've got 1, the repetitive typing problem. 2, enter FastKey, native and private. 3, the M1 versus Intel trap. 4, decoupling, UI meets engine. And 5, clean code and faster workflows.
All right, section 1, the repetitive typing problem, wasting keystrokes. Let's start right at the surface with a frustration that, honestly, we literally all deal with every single day.
Seriously, ask yourself, how much time do you waste typing the exact same AI prompts, standard email replies, or code snippets day in and day out? You're just typing them over and over. Now imagine if you could literally get all those keystrokes back so you could focus on your actual deep work. That friction, that is exactly what inspired FastKey. And here's a fun fact before we look at the solution. This elegant little tool was actually co-developed with AI, specifically Gemini and anti-gravity. It's a perfect example of using AI to build systems that make interacting with AI even faster.
And this brilliantly illustrates the solution right here. Notice how typing a tiny abbreviation, like 4TLC, instantly expands into the full AI prompt. Translate it to Chinese. It completely eliminates that repetitive friction, or typing 4GW and having it expand to George Wang. It's designed to replace long, tedious typing with instant text expansion, just continuously monitoring your keystrokes right there in the background.
Moving right along to section 2, enter FastKey, native and private.
What's really interesting is how FastKey solves this problem natively for macOS without adding a bunch of bloated software to your machine. It features global listening, meaning it works no matter what app you're currently typing in. It has an intuitive GUI to manage your shortcuts dynamically, and my absolute favorite part, real-time engine sync. It automatically reloads your local shortcuts file every 2 seconds. So if you make an update in the GUI, it's instantly available. No annoying application restarts. Plus, it rocks native Apple aesthetics, flawlessly supporting light and dark modes with those nice squircle icons.
But here's the absolute crucial point about its architecture. Unlike so many modern tools that constantly want to ping the cloud, FastKey operates entirely locally. Your keystrokes never leave your machine, zero telemetry, absolutely no external cloud dependencies, just complete data privacy and ultra-low latency. Section 3, the M1 versus Intel trap, a cross-machine nightmare. Now, building this native, local-first experience across different Apple hardware led to what a recent Gemini AI audio overview called a classic developer nightmare.
See, the developer was building this project across two totally different hardware architectures, an Apple Silicon M1 Mac Mini, which uses ARM64, and an Intel-based MacBook Air, which uses x86-64. Think of the M1 and the Intel chips as speaking two completely different languages. You can't just copy-paste a translator trained for one into the other. And when you're doing Python development, this creates a massive trap. We call this the virtual environment trap. People usually think of Python as just plain text scripts, right? But major packages actually use compiled binaries and C extensions under the hood. So if you try transferring or syncing a single python.ven folder across these two chips, everything breaks. Architecture-specific binaries for libraries like pyvinput, which handles the low-level keyboard listening, or Pillow for image processing, will just catastrophically fail if you mix them up. And it gets crazier. As the Gemini audio overview highlighted, they ran into a massive low-level Cocoa hijacking disaster. The developer tried to dynamically change the ugly default Python macOS dock icon into a nice Apple-compliant squircle shape by hacking directly into low-level AppKit methods right from the Python source code. The result? macOS completely rejected it. It threw a highly abstract, native NS invargument exception and instantaneously aborted the entire application. Just a brutal, flat-out rejection by the operating system. So how do you fix that? Section 4, decoupling. UI meets engine. To solve these chaotic OS crashes, the developers had to radically separate the application's brains from its brawn. Think of it exactly like a restaurant. The custom Tinter GUI is your front of house. It acts as the master controller, managing your configuration data and taking your shortcut orders.
When you click Start, it safely spawns the background engine. That Pineput background engine is the isolated kitchen. It's a headless worker process that securely hooks into macOS to execute the actual low-level keyboard commands completely isolated from the UI code. So how does this isolated kitchen actually cook up an automated workflow? Well, the headless engine securely listens globally, keeping a rolling buffer of your last 20 characters. Once it detects a match ending with a known abbreviation, it halts. Then, it simulates a rapid sequence of native backspace keystrokes to erase your trigger and instantly types out the full expansion, faster than humanly possible.
Which brings us to our final part, Section 5, Clean Code, Faster Workflows.
Emerging from that technical abyss of crashes and environment traps, the developers achieved stability through 3 core principles. First, absolute environment isolation. They created separate project baselines per chip architecture. Second, clean asset preprocessing. Instead of hacking the OS for a pretty icon, they pre-formatted their image as a true 512 by 512 RGBA PNG with an Apple-compliant Squircle mask already baked in. And finally, deployment separation. They kept their source code execution purely for development and let PyInstaller handle the heavy lifting of the final macOS app packaging and OS-level aesthetics.
So as we wrap up this explainer, I really want to leave you with this final thought. Whether you're looking to get your own keystrokes back with an awesome tool like FastKey, or you're building your very own cross-platform Python projects, remember the core lesson here. Are you properly isolating your chip architectures? Keep your code paths clean, keep your environments siloed by hardware, and whatever you do, please, never try to hack the OS from your raw source code.